we find approach to area and slope common in geometry and calculus. While area is the size in 2 dimensions, slope is defined as ratio or comparison between them, and a function is a mapping between them where one is as input and other as output. It is easier to measure the area of specific dimensions or with specific relations, but difficult with intermingled ones, like this shape, to approximate the area. The approach we take here is just using the more precise scale or so-called method of exhaustion. It is analogous and even perfect to measure the area of the pot in the picture with squared pixels, and eventually collecting them to perfectly come up with exact area. This can be easily shown with the sign of an integral as follows. Integration works like this in approximating the area. Let's take a linear function such as y is equal to x, marking the area under it. The function is linear, and by substituting random inputs, function produces specific outputs. For y equals to x, the input will be the ultimate output, such as 1 to 1, and 2 to 2, and ahead, making intervals on x shown as delta x and multiplying the altitude or y component to form rectangles, and eventually adding them up. We approach the area the best way, making delta x the smallest as shown as dx. We approach maximum accuracy, and the formula becomes as follows. So integration in a nutshell becomes summation of fitted rectangles in an irregular shape. There are different formulas too, with different types of evaluations, and they do evaluate perfectly. Graphical ones, representing shapes, and numerical ones resembling sequences. Integration is not only confined to geometry, it has vast applications in dynamics, finding instantaneous velocities, and their comparatives in motion.